So we're going to start with radioactivity, and first let's understand how to detect radiation or to detect any type of radiation. So there are three types of radiation. The first one is going to be alpha, then we have beta, and then we have gamma. So alpha is basically a helium nucleus, which is represented as the Latin symbol A for alpha, 4 and 2. What is this 4? What is this 2? We'll get to that later. Simple basic chemistry representation for the nuclide notation, but we'll get to that later. Then we have beta, which is 0, -1, and then we have gamma, which is 0, 0. So there are three basic radiations that we want to detect with the help of an instrument. And the first instrument that we have over here is known as the GM tube, or the Geiger-Müller tube, with the spark counter or with a counter attached to it. Let's try to understand how it is being constructed, and then we can move on from there. So this is what a GM tube looks like to a common person. It's just like a small tube which is transparent and just waiting for radiation to be absorbed or radiation to be let's say exposed to from the environment. So radiation could be coming from the environment from any angle through this window, and it's going to have some effect on the argon gas that is held inside the tube at low pressure. So what happens is that if we have argon gas, for example, let's do it in this way. Let's say that we have argon gas. So what happens with that gas is that it breaks down into two parts if it receives these radiations. So that process is known as ionization. That process is known as ionization, right? And in this process, what happens is that a stable atom of any gas, could be nitrogen, could be argon, could be any other gas, but we're choosing argon to be noble gas and to be non-reactive to the other elements of the environment, so that's why we're choosing argon. So this is just a simple argon atom. It breaks it down if it receives alpha, beta, or gamma, or any radiation. It breaks it down, this atom, into two separate entities. So it breaks it down into a positively charged atom and a negatively charged electron. So what it does is that it knocks out one electron from the valence shell upon receiving, and that electron becomes a separate entity, and the rest of the atom becomes a positive entity. This process in which a simple air molecule or simple gas molecule is broken down into two parts or into two separate atoms is known as ionization. You can further read about this definition from the book or from the slides that I will send you, right? So, but for the sake of understanding, this is what ionization actually looks like. A simple air molecule or a simple gas molecule will be broken down into two entities, which is positive and negative. And negative is generally the electron that has been knocked out of the electron shell, and positive is generally the atom itself, which is now left behind. And it's positive because overall the net charge on this atom would be positive because of the dominance of more number of protons in the nucleus, right? Okay, so this is what the GM tube looks like, and this is how it's operating. So what's happening is that upon receiving the radiation, the argon atom is converting into a negative entity and a positive entity, and of course it's happening many times each second. It's not just one atom, it's many atoms doing the same job at the same time. So the negative entity, we realize that one of the parts of the GM tube is positively charged, so the negative electron actually sits down or gets attracted to this anode because of opposite charges, and the positive charge is attracted to the body of the GM tube because it is negatively charged and the atom itself is positively charged. So when this happens, let's say that the positive charge sticks to the wall of the GM tube, but the electron actually starts traveling through this external circuit because it is an electrical circuit, right? And instead of this resistor, what we have over here is a simple counter represented as C. Although resistor just serves us the purpose of changing the value of the current, but it's already too low. We want all the current that we can get from the experiment to properly see it. So this is C, or you can say this is our counter. What the counter is expecting is the number of electrons or a few electrons passing through it. So as a few electrons or even a single electron passes through it, it will show us a reading. Now generally, since radiation or the levels of radiation are too high, this ionization process is not only happening with one atom, rather it's happening with many atoms. So there are many electrons or many atoms actually flowing through the circuit, and this counter is actually counting all those parts. It is basically an ammeter, or a slightly more complicated form of an ammeter, but this information is not a part of the course. This is just extra information for your understanding, that the counter is basically an ammeter, or at least representation of an ammeter, right? Okay, so what it's doing is it's expecting electrons to flow through the circuit, and as they do, it's going to count the values, or it's going to give us or generate at least a counteractive reading for the process. Now, when it does, or when it does complete the circuit, it moves through the battery, moves through the circuit, and then reaches its own pair that it actually came from. But of course, it does not complete the circuit like this one. What it does is that if an electron does get absorbed at the positively charged anode, since there is one more electron in the rest of the circuit, one electron actually gets emitted from the negative terminal of the battery because of the abundance in the total number of charges. So as one electron enters the anode, one electron also exits the cathode due to the abundance, and that immediately neutralizes the argon atom, and the argon gas, or the atom, resumes its life through the gas tube as a neutral atom, or as in this way. So what's constantly happening is that the argon is actually breaking down into a positive and negative entity and then quickly combining back again as a neutral atom. So this process of continuously breaking down and joining together is noted by the counter, and if the radiation is strong or very high in number, then this process will be happening more frequently, eventually leading to a higher value on the counter. If the process is happening less frequently and the radiation level or the energy of the radiation is less, then the counter would be receiving less number of electrons due to the ionization process. So the counter over here is actually giving us a direct relationship between the idea that whether we are receiving high radiation or whether we are receiving less radiation. So keeping all of these things in mind, this is how we actually detect radiations, right? Then we have another instrument for radiation detection, and that is the cloud chamber. This is another part of the course, cloud chamber. So the respect or the idea of this chapter would be basically to memorize everything that you know about the life or the qualities of alpha, beta, and gamma. That's the whole purpose of this chapter, or you can say at least 50 to 60% the purpose of the chapter is you memorizing what these qualities or characteristics will be. So you can answer simple questions based on these facts. Now, ionization power, of course, this is what we've done, and this is what we've understood just now. Now let's try to see, based on the same idea, what happens in a cloud chamber if we had an experience of alpha or beta or gamma. What's going to be observed by any person in the cloud chamber if it was experiencing these three different radiations separately. So if alpha was being introduced in the cloud chamber, or the cloud chamber has a very weak, you can say, under low pressures, we have a low concentration of alcohol vapor, and the tracks that we are seeing are because of the moving radiation through the cloud chamber. It's a transparent glass container that has these conditions. So what we see for alpha is thick straight tracks or thick straight lines. You're supposed to remember this, that if the examiner asks you in P1 that what may look like, or what output of the cloud chamber may look like to you if we had let's say an alpha radiation, so it would be a thick straight track or a thick straight lined track, which of course has a small range. So this actually travels to a very small distance. Alpha has a small range, and the reason it has a small range is because of its size. It's very huge in comparison to beta and gamma, so it collides with many air particles on its way from the point it's generated to the point it actually ends its life. So since it's very large in size, the frequency of it colliding with the air particles that are already present inside the gas chambers is very high, so it doesn't have, or it is not possible for the alpha particle to actually continue its life for a longer distance. And if we were to expose beta radiation or beta particles in the in the cloud chamber, we would see thin curvy tracks in the cloud chamber. This is what you will see, but the track pattern would be a bit longer. This would be a bit longer, and this would be short, thick, straight lines, right? And the reason for that would be that beta is very small in size and has a longer range than alpha, right? So now we move towards gamma. Gamma is the tricky one. It's hardly detected anywhere on any tube. Under very special circumstances, we'll have to detect it, or we have to find it. Otherwise, it's difficult to get any response from gamma radiation. So it has a very little effect of ionization, but whatever that effect is, it's very difficult to see in a cloud chamber. So it has little to no tracks. So if there is something like that, we will consider this as at least gamma radiation, or at least background radiation, or at least name it in this way that it's entirely gamma radiation, or there may be no radiation at all. That's the problem with gamma radiation, that detection is so difficult that sometimes scientists do ignore the fact that it's possible that there is gamma radiation, but we find it difficult to detect it. But how is it being detected then? If it's difficult to detect, then how did we find it out? Basically, for gamma radiation, under special circumstances, the radiation does produce a very small amount of radiation or small amount of reading on the GM tube. So we have to increase the value of the DC output to a very high voltage, and under those circumstances, when there is a very high potential difference between the anode and the cathode, there is a very strong electric field. It becomes easy for the argon atom to actually distribute or destroy itself to become an ionized particle. So some extra help coming from the increased voltage of the source, and then by any chance, or by random chance, the gamma radiation may sometimes break down a few atoms or so and eventually produce a reading. So this is what a GM tube does, and this is how it's used to see whether we are getting alpha, beta, or gamma. But now there is another problem. The problem is that the GM tube cannot discriminate between alpha, beta, and gamma. All it can do is just give you the reading of the radiation it's receiving. It cannot discriminate or distinction between, or create a distinction between alpha, beta, and gamma. It's not its job. So in order to do that, what we do is what we've found. The topic that we're going to look at is the penetration power. Like in this term, that how alpha, beta, and gamma, what capabilities do they have in order to cross simple matter? Can they cross matter, or can they not do that? Now again, to remember this, I would recommend that if you remember all of these radiation with the respective sizes, it becomes easy to remember all these properties, and there are many of them. So alpha is large in size, beta is small in size, and gamma has no size. So if the alpha particle is very large in size, so the chances that, or the possibility that it's going to collide with a matter or with any matter and then immediately stop, are very high, because the size is so big that it's difficult for it to pass through any matter. So to understand this better, what we do is we generally, you will see this MCQ in the examination, that we introduce alpha radiation, we introduce beta radiation, and we introduce gamma radiation, right? And see what happens with the GMT. So to stop an alpha particle, it's going to be good enough if you just placed a piece of paper. So if you have a piece of paper or cardboard, if you place that in front of an alpha source, cardboard, you will get no reading after placing the GM tube over here. So what we're trying to see, what we're trying to detect, if I had placed the GM tube over here, I will get no reading if it was alpha. But if I had placed the GM tube over here, I would get the reading on the counter. So if after placing the piece of paper, the reading reduces abruptly to a very low level, that means that the source contained alpha particle. That is how we guess that whatever radiation is coming from the source, we don't know. But if you want to guess it, or if you want to predict it, then you can simply start with placing a piece of paper. If the reading is not affected by placing a piece of paper, that means there is no alpha, and we continue our journey to figure out whether it may be beta, right? So we are worried or we're concerned about the gamma the least. Why? Because it can pass through all matter, all materials, everything. So we know that it's not going to be stopped easily. It's unstoppable, quite frankly. So we will check it at the end. So now what we do is we place the GM tube over here again, and we see that the reading is not dropping even after placing the piece of paper. So then we place a piece of aluminium sheet. We place a thick aluminium sheet. So it could be any metallic sheet that should be of more than 5 millimeters of thickness, so 5 millimeters and so on. It could be aluminium, could be copper, could be brass, could be iron. So any metal or any metallic sheet with 5 millimeters or more thickness is good enough to stop the beta radiation. So before crossing the sheet, we take a measurement, and then after crossing the sheet, we take another measurement with the GM tube. And if we find a difference in both readings, or after placing the metal sheet, we see a difference of reading. For example, previously it was 800, and now it is at least 700, 600, 500, or at least even 450. This major reduction in value suggests that this source, this unknown source, contains beta. But if the reading does not reduce from this value to a very low value, for example, it's very possible that the reading shows after placing the piece of paper is 790. So this would not signify that this contains beta particles. Why? Because the values keep on changing due to the random nature of the radioactive process. What is randomness? We will get to that later. So to get a confirmation, there should be a very drastic change in the value of the counter. Okay, so for example, if we still don't get a reduction in value, that means that there must be another radiation, that is gamma radiation, which we test at the end by placing a thick lead sheet. So there is no specific thickness of this, so thick lead sheet would generally, up to O levels and IGCSE, generally stop the gamma radiation completely. But when you go to A levels, you realize that it only helps reduce its strength or intensity. It cannot stop completely. It cannot help stop the gamma radiation completely. It's possible that over here, if the atoms or the radiation counter that we're getting is 1000, it's possible that over here it may be toned down to 250 just by placing the lead. Now the problem over here, why didn't we start with the lead at the beginning? The problem is that lead can absorb everything. Lead can absorb alpha, beta, and gamma. So if you started off with lead, you would not be able to differentiate because it can absorb everything. So we will start with the smallest one first, that is piece of paper, the thinnest piece of material. If something changes, that would mean that it is alpha. If nothing changes and placing aluminium sheet or placing a copper sheet causes a change, that would mean that it is beta. And if placing a thick lead sheet produces a change, that would mean that it is gamma. Now one more thing, that for example, if aluminium sheet is good enough to stop beta, then it is also good enough to stop alpha. So again, the point would be never to start with your extreme case scenario at the very beginning, because we are still expecting that it may have alpha in it. So if it does have alpha, we would need to give it the due chance to actually express itself before crossing a material. So we always start with the thinnest one, that is paper or a piece of cardboard. Then we move on to thicker materials that are going to eventually stop or be able to stop beta and gamma. So that is how we use the GM tube in junction with physical materials on the outside. This is the diagram that we're looking at, right? This is what we're discussing right now. So this is the way we are going to use the GM tube to understand, and physical materials, to fully understand what type of radiation we are working with. So you can see that the beta particles can successfully cross the thick piece of paper. They can successfully cross through air as well, but they are unable to cross through thick metal sheets. Similarly, gamma radiation can pass through everything. They can pass through air, piece of paper, no problem, aluminium sheet, no problem, but they can be stopped by, or their intensity can be reduced greatly by placing thick lead sheets. But over here we can experience that alpha particles, already too big in size, they have a difficulty passing through air even, so how can they pass through the piece of paper? So that is how you can counter logic, or you can develop a counter narrative and develop at least some sense to the question, and try to memorize all these points in terms of their relative penetration powers. And this part actually deals with the range of the particles, and we also need to memorize that. Why do I need to know the range of the alpha particles? Because it will help us design a few experiments in which, if I know that the source is purely alpha, then I don't have to be as safe as compared to beta or gamma. I don't have to wear all the safety equipment. All I can do is maintain my distance, that is at least 10 to 20 centimeters away from that, and I will be safe. Similarly, we need to know the range of beta and gamma. Gamma approximately have infinite range. They can travel as far as possible, as long as possible, because lead sheets or thick lead sheets are not available for everyone. We have not surrounded our houses with that. We are not wearing a lead suit right now, so we can't stop the gamma radiation coming to us. But the catch over here, or the idea over here, is whatever radiation we have in the surrounding or in the environment is so low that it's not fatal to us right now. But of course, if we stand too close to a radioactive source, and if it is by mistake or any chance emitting gamma radiation, then of course it's eventually going to cause cancer. So overexposure to the radiations is going to cause cancer, redness of the skin, and cataracts in the eyes. Redness of the skin and cataracts are much milder conditions, but if the exposure is too high, then eventually it's going to lead to cancer. So what we have looked so far about the alpha, beta and gamma is their penetration powers, their relative ionizing effect, right, and their behavior in the cloud chamber. Now we're going to look at the nature of the radiation. When he says nature, it means what are they made of. So the nature part, or the nature of the radiation, actually is asking you what it's made out of. What do you see, or how do you see that? So alpha is basically treated as helium, not the atom, but the helium nucleus only, or the helium nucleus which is stripped off of its electrons. It has no electrons, it only has a central nucleus which has 2 protons and 2 neutrons. All this information has to be memorized by you as a student. And beta is taken as an electron, pure electron, and gamma is an electromagnetic wave. You may remember that we did gamma radiation up to the radio waves and their uses for that. We did that in our previous lessons. So from that spectrum, one of them was gamma radiation. It is more energetic than an X-ray. The only identity gamma has is its comparison with the X-ray. It doesn't have an individual identity. All we know about gamma radiation is that it is stronger, or it is more energetic than an X-ray. And so you will find that the uses of X-ray are somewhat similar to the uses of gamma ray, apart from some differences. X-rays can be used for human being bone structure, to view that, but gamma rays can't be used for that. We can use it to produce a bone pattern, but the energy of gamma radiation will be so high that it will eventually cause cancer, and it will be harmful to expose anyone even with a tiny amount of gamma radiation. But Other than that, all the uses are approximately the same. We use it to kill cancer, we use it low level of radiation or low energy radiation of X-ray and gamma radiation for radiation therapy to the cancer patients, and we also use both of them or radioactive sources to detect metal cracks. That we have discussed all these points in the electromagnetic spectrum. So the identity of gamma radiation, it's not individual, it's not independent, it's actually dependent on the X-ray, which is of course more energetic or more energetic than an X-ray. And the other representation that we're looking at in terms of chemistry is known as the nuclide notation. So whenever we write down all these elements in physics, we are following the chemistry's way of writing down the names of the element. So you remember that, for example, if I take sodium, that is Na2311, right? This representation is known as nuclide notation. So for example, if the sodium atom loses one electron, so it eventually comes to look like as this one, Na plus 1 with 23 and 11. This representation way or the method is known as nuclide notation. So similarly for alpha and beta and gamma, we have nuclide notations, and to see that, this is where we actually started off from the very beginning. This is what I wrote down for them: alpha, beta and gamma. But we're going to write down for a few more. So alpha is represented as 4, 2, beta represented as 0, -1, gamma represented as 0, 0. Then we have a proton. Proton is represented as 1, 1. Neutron represented as 1, 0. Now, what do these elements represent? The one written at the top and the one written at the bottom. So the top one is the nucleon number that represents the total number of protons plus neutrons in the atom. The lower one represents the proton number only. Proton number, that would mean that how many protons do exist in this atom. So since we're dealing with nuclear physics, we are not concerned with the electrons or how many electrons have been lost or gained. That is chemistry. That is what chemical reactions do. So in physics, we are interested in the nucleus. What happens with the nucleus itself when all the electrons are stripped away, or all the electrons are not a part of our discussion? What's going to happen? So if I look at over here and I want to predict the number of protons and neutrons in any single one of them, what I can do is, for the protons, for example, if I want to predict this for alpha, this will be 4, 2, protons, neutrons and electrons. So the lower number represents the number of protons and the number of electrons if it is neutral. Neutral would mean that the number of protons are equal to the number of electrons. So if I have the information about the protons, 2 protons, then I can also communicate that there must be 2 electrons. But then again, this is not a part of our discussion. Electrons or their issues or their changes or any exchanges between the atoms is not a part of our course. That is chemistry. Over here, what we have as neutrons is, since the upper number represents both protons and neutrons, what we can do is just simply differentiate, or we simply take the difference of the upper number with the lower number, so that protons can be subtracted and we are only left with the neutrons. So what we get over here is 4 minus 2 equals to 2 neutrons. This is exactly what we did for the alpha, that it has 2 protons and 2 neutrons. Now let's apply the same exercise for the sodium atom that we have over here. So sodium is 23 and 11. So if I had to mention protons and electrons, I will just look at the lower number and I will say that they are equal. If I had to write down the number of neutrons, I have to take the subtraction of the upper number with the lower number. So 23 minus 11, that gives me 12 protons. Sorry, 12 neutrons. So the number of neutrons inside the atom will be 12, and the number of protons inside the atom will be 11. The number of electrons on the outside of the nucleus will be 11, if this is neutral. Similarly over here, if you wanted to predict all of this, then the protons and neutrons, let's predict that. The number of protons will be 2, the number of neutrons will be 2. No point discussing the number of electrons. If you do want to write this down, that will also be 2, because they have to be equal to the protons. Similarly over here, there are no protons, there are no neutrons, there are only electrons as one. The quantity of the beta particle is that itself is an electron. Gamma radiation has no proton, no electron, no nothing. It has basically no charge. It has no identity. And proton, of course, is going to be one. There is no neutron, there is no electron. It's only alone or in a standalone configuration, just one proton. Again, if we look at neutron, this is proton will be 0, neutron will be 1 in terms of quantity, and electron will be 0. So it's a standalone neutron. That's why it's going to look like this. So whatever we've done over here, this is the calculations related to the nuclide notation to find out the number of protons, neutrons, and electrons. And I'm sure that you've done this already in chemistry as well. So this is what we understand about the nature part of the alpha, beta, and gamma. You're supposed to memorize all of that. You're supposed to memorize the nuclide notations of alpha, beta, gamma, protons, and neutrons. We will need them when we go ahead with nuclear decay equations. Okay, so we're done with penetration power, we're done with the ionization power, and of course the mass. The mass would only mean how heavy they are. So we already know that it has 2 protons and 2 neutrons, the alpha. So it's going to be at least 4 times heavy than a proton. If we know that protons is equally massive than a neutron, which we are taking as an assumption, not every time, but as an assumption, so it's as good as 4 protons or 4 neutrons, right? So if I come back over here as to the electron is approximately 1840 times less massive than a proton. If you do want to know about the mass of the proton, that is approximately 1.67 into 10 raised to the power minus 27 kgs. The value is not required. I'm just sharing this for your information. The mass of an electron is even less than that, which is 9.11 into 10 raised to the power minus 31 kg. So if you take a comparison between 1.67 and 9.11 and you divide both of these values, you will get approximately 1840 as your answer, which for the sake of discussion we will say that it is approximately 2000 times less massive than an alpha particle, or the alpha particle is approximately 1800 times or 2000 times more massive than an electron. So no matter which way you put it, this is how we can say that. And gamma radiation primarily has no physical mass. It has no charge, it has no mass, right? So we are done with mass as well. We are done with ionization power. We are done with the nature of radiation. I will share the notes of this lesson or this PDF with you. You can do this on your own as well. Now we move to nuclear equations later on, but let's complete the common properties that as much as we can before ending the class. So what's the charge? The charge on an alpha particle will be positive 2. Why? Because it is containing 2 protons and 2 neutrons. Neutrons are neutral. There is no charge on them. Protons overall have a positive charge. So since this is just an atom, we are not concerned with the electrons. This is just an atom. We will consider that to be a positive charge. So the alpha particle is positively charged. The negatively charged electron has a negative charge on it, which is equal to the charge of the electron. And again, if you move towards gamma radiation, they have no charge. Partly because this is why gamma radiation, or you can say the gamma radiation coming from any source, is difficult to detect because it has nothing to offer. We can't exploit anything. We can only exploit the GM tube under special high voltage circumstances to see, or to be at least able to see, whether there is something in terms of gamma radiation or not. Okay, so then we have their relative velocities, how fast they're moving, and the speed of light, which is c equals to 3 into 10 raised to the power 8 meters per second. What he has done, he has written down all velocities in terms of the speed of light. So when we write down that the alpha is at best 0.1 times c, that means it is 10% the speed of light. That would be approximately 3 into 10 raised to the power 7 meters per second, much lower than the rest of the particles. Beta, and of course all of this is due to its high mass. It's very massive, so its own speed is very low, because we end up with kinetic energy calculations, and kinetic energy has half mv squared, mass and velocity both. Since it's very massive, The velocity is approximately lower than the rest of the particles, but they will have enough energy to cause cancer or to at least cause ionization. We'll get to that later. On the other hand, we have beta particles, which have approximately 99%. They are so fast that the highest speed recorded of them is that they do approach the speed of light, just good enough or just shy of 0.01, or you can say 1% of the speed of light. They are very fast. And then we have gamma radiation. They are moving at the speed of light, because when we did electromagnetic spectrum, we did understand that all of the spectrum is moving at the speed of light at all times. So these are the properties